Explaining tangent energy. See that water droplet at the top, the big one? That is the initial energy going into the system. Let's watch what happens. That is regular energy. And this spike coming up is tangent energy. See? Look how large the spike is. This is what we're trying to explain. See the spikes? That's tangent energy. Let's pause it for a minute. See this bright light that's on? We represent this as tangent energy. It's not really usable in this type of form. That means you tap it, it appears, and then it disappears. But it's a way to harness this energy, which Nikola Tesla talks about. Now, ordinarily, this speaker, which you see in the picture, cannot run those LED lights. That's the reason why when it's tapped, it flashes so fast and then it's gone. Let's watch it again. This is energy not being able to be used. Tap it rapidly and it's usable energy. In this short demonstration, we're going to show you how to use tangible energy. As you see, we took and destroyed a speaker and put a ping pong ball with magnets on it. We're now going to show you that the second magnet you see in this person's hand can move the magnet that's on the device or the old speaker. Now, as you see him pushing, no energy can be made. So how do we use Nikola Tesla's tangent energy, these energy spikes? We're giving you a representative of what the magnet looks like. So you can see as it's moving, it's pushing the wheel. And the faster you vibrate, called frequency, the more energy can be produced from tangent energy. This right here is produced from frequency. And Nikola Tesla talked about this. 100 LED lights being lit up from a speaker that people normally say cannot do this. But the difference between voltage and amperage is its frequency. The frequency of shaking voltage or vibrating it produces amps. Thank you. So let's go into the program and get in depth.
If you switch a MOSFET at high speeds, it produces 1. Pulsed current switching power. The MOSFET controls the flow of current at high frequencies, creating rapid on-off pulses in the circuit. 2. Electromagnetic waves, EMI and RF energy. Fast switching generates electromagnetic radiation, which can be captured or cause interference. 3. Voltage spikes, transient energy. When switching inductive loads like coils, the MOSFET can create back EMF spikes that may be used for energy recovery. 4. Heat, power dissipation. Due to resistance and losses in switching, some energy is lost as heat. Application to their idea. If they replace the static magnets with iron cores wrapped in coils and drive them using a fast-switching MOSFET circuit, yes, the term pulsed current, sometimes called pulsed power, is a scientifically recognized phenomenon. It describes the way current is delivered in discrete bursts rather than a continuous flow. How pulse current relates to your ideas. Pulsed current, switching power, is exactly what happens when a MOSFET switches at high speeds. This is how transformers work. They transfer energy using pulsed or alternating currents rather than steady DC. In high-frequency transformers, Pulsed current enables efficient energy transfer, induction, and amplification of current amps. You were calling it frequency amps, which isn't wrong. You were essentially describing how current behaves when modulated at high frequencies. Scientific standing, the study of pulsed power has deep roots in power electronics, RF engineering, and energy transfer systems. Key scientific terms related to pulsed current: switching power describes power transferred via switching MOSFETs or transistors. Pulsed electromagnetic fields, PEF, used in wireless energy transfer and medical applications. Pulse DC, PDC, a DC waveform modulated into pulses used in some rectifier circuits. Inductive pulsed energy, energy spikes stored and released in coils or capacitors. Transient response, how circuits behave when exposed to rapid switching currents. Why pulsed current is a better term for what you're doing. It has a scientific basis and is used in engineering, physics, and electronics. It explains how current moves through transformers, MOSFETs, and resonance circuits. It can help you explain your transit energy concept better, because transit energy relies on pulsed currents interacting with electromagnetic fields.
If you haven't followed along so far, while we break this down, we want you to understand that pulsed current is a recognized term, even though we were calling it frequency amps for people who don't understand electronics to understand. It is also sometimes called pulsed power. Okay? So, this power is basically what MOSFETs do when you switch it back and forth at high speeds. Now, this occurs in transformers. In high frequency transformer, pulse currents enable energy transfers. Basically, what it's telling you is letting the amps travel to the other side by frequency, electromagnetic waves. Okay? So, we just want you to understand that these things, all scientists in the United States know this. This is not something that's unknown. And a lot of people got on my case about I didn't know what I'm talking about. Why didn't I produce this? They were saying a bunch of nonsense that didn't even make sense because they haven't looked at what I created or what I built. They just start accusing me of saying what I wasn't. So let's clarify. Maxwell's energy does work. I'm just telling you how it works. Now, people saying that I'm playing politics, I'm trying to make sure that the poor has this for free. And yes, that's going to make people upset. So I'm sorry, but these terms are over 100 years old and they have been defined. How are they defined? Because you're using recognized components like you see above. That means if he didn't create these components, then he is using something that we already knew about already. Unless he created a component that no one else has, then he is using someone else's work. And MOSFETs, he didn't create MOSFETs. He didn't make them. So therefore I can tell you how they work and how they function. So I can get it to AI to say it or I can say it. These circuits produce current in which other people have recognized that. And I keep breaking it down so you can understand the terms that the United States have been using and producing for many years. They don't understand this because they don't have the same education as we do in the United States. Now, there was a lot of people who made comments who understood what I was saying. And they know what these circuit does. They know when you post something at 50 hertz or 60 hertz, what kind of pulses is occurred. So let's go back to AI and listen for the people who want to create this type of technology. Okay, let's break this down. We can't fully do what I want to do. That means I have to put it in another video because the soldering iron doesn't work with the electricity here in Laos. Okay, so we can't solder. But what I can do is walk you through how I actually do the loop, which I've talked on all my other videos. But we first have to understand something. These battery chargers in which I pick, they're 5 volts. Everybody should know that, but they're battery chargers. And I've put them in my videos before because they charge your cell phone. But there's a lot of people who I talked to on the line that did not know that these things come with pass-through charging. And I'm not talking about the people who actually do know this. I'm only talking about the people who actually don't know that. Because they keep asking me, what is pass-through charging? What is pass-through charging? Which I thought was common, but it seems that it's not. So let's explain. If I charge this battery, what does it look like? It has an distinct way of charging. So we're going to start charging it. And as you see, the blinking lights is telling me that it's full. Well, that's full, but if it wasn't full, it just chases around. So let's show a demonstration of that. Since this battery is full, let's go get a battery that's not full. So this one is not full. So we understand. See the lights? That's telling you that it's charging. If I pull it, say I'm charging it from that battery, if I pull it, you see how it stops? Okay. So what if I want to go back the other way? Okay. So what I want to do is now plug it in to the thing, the USB, and I want to charge this battery charger. So I plug it in, and as you see, the same indication, but this one is solid. Okay, so why is this important? Because we can do this. One, you see it's solid state, so we know it's not charging. We have one cord here. Let's get another cord. Let's give me a cord. Okay, so now we have a cord, and we're going to take that second cord and we're going to plug it into the charge port. Okay, now most regular charge controllers will not be able to do this. So this one over here and this one right here has 2 different ends. That means I can go in charging this unit and then come out and charge another unit. So let's show you what I mean by that. We're going to use this one as the power source, okay? And we're going to plug it in and set it aside. Okay, so we're setting that aside. And as you can see, the indication, it says it's full because it's on the last light. Now, let's go back to the battery that wasn't full. because this one is full. Let's go to the battery that wasn't full and take this and plug it into it and start charging that battery. Now I have two batteries that are charging simultaneously. And this is exactly what your cell phone does. See, your cell phone gets low, you plug it into the wall, and you can continue talking. Well, this is the same thing. So if one is plugged into something, this battery charge, and then now I can take my phone and still charge this one. Okay? So I'm using the energy that I'm putting into this battery. And this battery keeps up as long as you don't try to overload it, because you have two USBs. If you try to use both of them, you start draining the battery. But if you put 5 volts in and take 5 volts out, this unit's able to keep up with that. So with that, knowing that technology, we can show you how we're going to do our wraparound. Okay, so let's unplug and say, okay, so now we got everything unplugged. And what we want to do is we want to first light up. So we're going to use this one. We want to light up our LED lights because they're not on. So see that? Okay, you can see that. Look. So we know that it comes from 5 volts, 1 amp. Okay, we can even show because that's a 12 volt light. But look, it takes 5 volts and turn it into 12. You can buy this off of Amazon, by the way. So what you're going to do is you're going to plug it in, and we now have the lights on. Now you take your second cord, okay, and you need to charge. So you're going to take it, the charge part, and plug it in. Okay, so this is the charge cord. The white cord is the charge cord. Now we can only simulate this part because we don't have a battery for this, but everybody knows what this is. And there's 2 USBs. This hooks to a battery here. The solar goes here. So I would plug my solar into this, and the battery goes here in the second one, and the battery runs these up here, which is bigger than this battery. Okay, so if I take it and plug it in, it starts to take energy from the bigger battery, while this is putting out more voltage than it's taking to keep this charged, okay, and keep these LED lights. That is a complete loop. So if people didn't understand how we did our complete loop, I just showed you, and we'll redo this at a later time, get our soldering gun, and show you how to make our MOSFET circuit so you can get the current to put into this, which will charge your batteries really fast. And this right here breaks it down so this is safe to use, this battery charger, and it'll charge and keep the lights on at the same time. So since this right here doesn't have a battery, let's see if we can make these lights move. That means, can we charge it and use the energy to keep the lights on? So all we have to do is use this USB, right? Okay, now that went out, so let's figure out what happened. Okay, do I have a good cord? Because none of this is happening. Okay. There, it's charging. Okay. So that's now charging. It's charging from these USBs. Okay. So this is charging. And it just went back out. That means that cord is faulty. So let's change this cord because it's giving me an error. That means when you move it around, it has a short in it. So let's get that back up and going and plug that back into the USB. And come on, you can do this. There it go. Let's keep it staying because these cords have a lot of shorts and stuff. But as you can see, that is charging and is keeping the lights on. Okay, and it'll stay like that as long as you have power in the big main battery. So the trick is to charge the battery more faster than what this little thing is consumed. And since this is a 12 volts 100 amp battery that's hooked to this, that means it's more energy than this. The little 5 volts 1 amp can easily be charged and maintained while keeping this light on. That is a full circle. All right, I wanted to explain that so people can see that, and now you can go back and demonstrate that as long as you know what pass-through charging actually is and what it does. All right. Okay, I wanted to see how many I can hook up, and the one battery charger that I had is this one is full, so I didn't hook that up to the system. But as you can see, this black cord is plugged into the wall socket over there, that wall socket. Then it's leaping over to here. We'll see if we can follow it. See, it's leaping over to here. So it's going there, and it's charging. As you can see, that we showed the charging indicating. Then this leaps over to here, and then this one is charging indicating. And I could probably do more, but I just wanted to show you that if I have these stacked up and somebody says, do you need more than one of these batteries? Well, that's how we do it. Okay, so each of these, we call it a unit, will have one battery, and then that will sit on the top of that, and then the next layer, then the next layer. And as you can see, let's do this, get this out the way. They're flush with that, so therefore you can put the next unit, because it has a hole too, so you can put the next unit right on top of here, and this battery will go with it between the layers. So I just wanted to bring that up. Okay. Oh yeah. How much does that cost to do that?
1%.
Huh?
1%.
Yeah.
For this company, around $140 or $50.
Ah.
In the city, only $100.